Okay, so in this video, we are going to change our topic to where the hypothesis is defined by an inequality. So as an example, I'm going to consider Starbucks iced coffee amount. So grande iced coffee is supposed to be 16 ounces. And by the way, this example was inspired by a news several years ago that someone sued Starbucks saying that like in iced coffee, there it's less than 16 ounce if you remove the ice. So like the main point is whether ice should be included in 16 ounce or not. And he claimed at the time in the lawsuit, he or she claimed the ice should be excluded when you count 6 ounce. So then Starbucks is giving me too little. So they are not doing fair trade, something like that. Well, I don't know how it ended up, but I think somehow maybe after that, I think Starbucks iced coffee had like less ice. Anyhow, so think about that. Someone sued Starbucks iced coffee has lower content, like a little too little than it advertised. It's supposed to be. So you are a Federal Trade Commission agent. You want to test it. Then in this case, you may imagine hypothesis test like this. Without any evidence, you believe that the amount of the iced coffee is 16 ounce, which is correct amount. And alternative is different from 16, right? Exactly. So you randomly get 100, you randomly order 100 coffees and measure them and see if their average is 16 or not. Something like that. And we know how to do it. You are going to reject if the sample average is smaller than lower critical value or greater than upper critical value. So you calculate critical value, 16 is here, calculate critical value, and outside is rejected. And then the rejection means Starbucks is doing something wrong. But that means the amount of the iced coffee is not as advertised. But the problem here is, do we need to punish? What happens if the actual amount is more than 16 ounce? Do we have to worry about that? Do you have to reject the null hypothesis? No. In this case, the main issue is whether it is less than 16 ounce or not. Less than or greater than or equal to 16. So in our hypothesis testing framework, I will reject the null hypothesis even if the actual amount is more than 16. But in practice, it's not a problem. So we are going to modify the hypothesis to this one. So depending on textbooks, some textbooks say this way. So in the null hypothesis, you believe it will be exactly 16 ounce. But an alternative hypothesis is that it's less than 16. So you reject the null hypothesis only when the alternative is true, less than 16 ounce. Or in other textbooks, the null hypothesis includes greater than or equal to. So it does not matter. These two are equivalent. In any case, simply like if the amount of the iced coffee is greater than 16 ounce, it does not matter. Or you may think it won't happen. Starbucks won't give you free coffee, free additional coffee, or whatever. Anyhow, we are not interested in what's going on above 16. We are only interested in whether it is exactly 16 or lower. So it's one-sided, and of course we reject the null hypothesis only on the lower side, only when the observation is significantly lower than 16 ounce, right? You understand? So if observation is greater than 16 ounce, like who cares, right? I don't mind having more coffee for the same bugs. Okay, so we call this one-tail test, right? The idea is simple. We are going to reject only on one tail, right? It could be upper tail or lower tail. It depends on the context and depends on the hypothesis you would like to test. So idea is simple. Upper tail test means the test where you are going to reject the null hypothesis if the sample average is too large. It must be small, but problem happens only when it's too large. So you can write it this way. And of course, the lower tail test is symmetric, the opposite. You reject if too small, right? Like Starbucks example, right? So in this example, of course, I'm going to use the lower tail test for the Starbucks iced coffee, but you can just flip the direction, the inequalities, plus minus signs to change it to an upper tail test. So I believe it should be straightforward. Later, we are going to do some exercise. Okay, so back to the iced coffee example. So this is the hypothesis we'd like to test. We don't even think about like greater than 16. That's not our concern at all. So we are going to reject the null hypothesis only if the sample average is too smaller than 16, significantly smaller than 16. So then we may use the same normal distribution we used before, but now we are going to have only one direction for the suspiciousness. So we only worried about this side. This side is not a problem. So previously I made red arrows on both sides, and I said like a negative shock is as equally likely as the positive shock, but now not. They are not equal. We only worried about negative shock, negative side, right? Only on this side is suspicious, right? Some problem. Okay, then we are going to calculate in the p-value approach. When you observe this point, p-value would be here. But remember, in the same situation, if you observe x bar here, in two-tailed test in the previous chapter, p-value included negative area and negative errors as well as positive errors. So we had to, at that time, p-value included two-side errors, but now it's only one-sided, right? That's the difference in the p-value. And then critical value will be also one-sided. In the previous chapter, and so in the earlier today, the critical values are two-sided. Upper critical value, lower critical value. But now, we only have lower critical value. Upper side is not a problem. Upper side, there is no limit. We don't reject on the upper side. We only concerned about the lower side. So the rejection region is located on the lower tail. So there is only one critical value on the lower side. And of course, if you are doing upper tail test, the critical value must be on the upside. Of course, that's simple. Okay? So then, let me compare three approaches. Remember, there were three approaches: t-statistic approach, p-value approach, critical value approach. So, like in those three approaches, we will compare one-tail test, lower one-tail test, and two-tail tests. So, t-statistic, in calculating the t-statistic, there is no difference. T-statistic is just neutral. It is just standardized difference. It does not say where we are going to reject, right? But the p-value, after calculating the t-statistic in the same way, but when you calculate the p-value, now it depends on what test you are using. So if you use two-tail test, remember we have like this. And in upper tail test, we are calculating probability only on the upside. So now we don't need absolute value here because it's only one direction. In two-tail test, we have to consider two cases. So I put absolute value, but now we don't need. And lower tail test is probability on the lower side. So again, t-statistic does not change, but depending on where you reject, your p-value must include the errors on the rejection side, right? Where you reject. So, and the decision rule is the same. You are going to reject the null hypothesis if the p-value is smaller than alpha. But so this part is the same, this part is the same, but how you calculate the p-value reflects where you are going to reject. So this part is the different. And as you can see, usually two-tail test has twice larger p-value because it includes errors on both sides. But p-value, like upper tail test has only one side, lower tail test only one side. But two-tail test includes both sides. So p-value are different. T-statistic approach. And of course, as I said, t-statistic itself does not change, but the rejection rule changes. Rejection rule changes, decision rule changes. In the two-tail test, you reject if t is smaller than minus something or greater than plus something, z alpha over 2. So your z alpha over 2 is the value that gives you alpha over 2 probability on both tails. But now, upper tail test, you reject only when t is greater than something positive. Of course, lower tail test will reject the null if t-statistic is smaller than something minus, negative. So they are one-sided, but also what's more important is the subscript alpha. You have to pay more attention to here. So alpha is the probability of type 1 error, or how much you are going to reject, right? So in two-tail test, if you are willing to reject, say, 10%, that means you will reject 5% from the lower tail and 5% from the upper tail, right? So you split the 10% rejection probability into both sides. But in upper tail test, you have to put all the 10% only on the upper tail. So z alpha, it's not alpha over 2. You do not split the probability half and half. Significance level is not split. Lower tail test, the same thing. So now this z value, the thresholds will change. T-statistic itself does not change, but the thresholds in the decision rule will change. Right? So the idea is the probability alpha, the significance level, is not divided on both sides. So you do not need to split them on both sides. So that's why the decision rule changes. Now, critical value. Two-tail test critical value was calculated this way. Center is the same. Everything starts from the hypothesis. But in two-tail test, a margin of error is allowed plus minus sides. Plus margin of error minus margin of error. But in one-tail test, margin of error is put only on one side. Like upper tail test, you're rejecting only on the upside. So you put margin of error on that side. But the other side, simply the margin of error is kind of infinity. I don't mind. Right? So same, lower tail test has negative. It's upper tail test has positive margin of error. Also, remember, look at this, alpha. Subscript is not alpha over 2. Idea is the same. You are going to put different margin of error because you are now focusing on only on one side. right? To match the same significance level, you have to change the z value for only one side. And rejection goes like this. So idea is this is pretty simple. Two-tail test reject on both sides. Upper tail test only on upside. Lower tail test only on lower side. So these three approaches need be modified slightly when you have one-tail test. But as I said, the idea if you understand the main idea, it's pretty straightforward. So I don't worry about too much. Just imagine what is going on, what you're doing, and think about the context where you are going to reject. Okay, so z alpha over 2 and z alpha, they are different. So these values 1.64, 1.96, 2.58, these numbers have been used for confidence interval and for two-tail test, right? So they are common numbers. However, when you consider one tail, the number has to change. So, like, this is confusing. So 1.64 was used for 10% significance level when you used two-tail test. But same number is used for 5% significance level in one-tail test. The reason is clear. So 10% will be split half and half, 5%, 5% on two-tail test, 5%, 5%. But in one-tail test, 5% one side is for significance level 5%. So 5% significance level is put only one side. So these two are kind of equivalent, right? So, and you will use these numbers a lot in the homework, and not only in this class, but in any following classes or your work, whenever you use the hypothesis test. So you will get used to them. Okay, so in the next slide, in the next video, I will go back to the example again, and we'll use more concrete numbers to apply the idea and see what changes in one-tail tests. Okay, thank you for watching. See you in the next one.